Bismillahirrahmanirrahim. Assalamu alaikum. I welcome you all to lecture number 15 for the course of control system. My name is Engineer Jaffar and I'm instructor for this course. So as we all know that this is the second part of lecture number 15. Let's start with the recapitulation of the previous part, in which we have started the discussion about the root locus. That what is root locus? We have introduced ourselves to the root locus. We have also done the angle and magnitude criteria that are used to make sure that this specific point is on the root locus or not. Then we started the construction of root locus, in which we have done first two steps. These were all the slides that belong to the first part of the lecture, and let's go towards that topic which was left in the previous part. So this was the first step. In this first step, you have to basically plot these roots on this x-axis or even the y-axis if it is mentioned. So but the roots here are basically real numbers. So the first root is at 0, the second one is at -1, the third one is -2, and we followed that. The second step is basically to find either these points are basically on the root locus or not. So this P1 was not on the root locus because it does not satisfy the equation that was there for the angle criteria, that the sum of the angles should be equal to the odd multiple of 180 degrees. So it was not here because it turns out 0. The second point was this point P2, and this point was on the root locus because there were two on 0 degrees and this one was on 180 degree. So this point basically was on root locus because 180 is the odd basically multiple. You can see that this is 180. So this point was on the root locus, and the third point was this point P3, and this P3 was not on the root locus because you see that this is 0 and there are two 180s on this side. So 2 180 means this is not an odd multiple of 180. This is the even multiple of 180 because the sum turns out to be 360, and 360 is nothing but the even multiple of 180 degree. So this point P3 is not also on the root locus. We discussed that, we have established that. You can see that this is 360 and 360 is nothing but the even multiple of 180. So that's why this point P3 is not on the root locus. Let's take point 4. So point 4 has no pole on this side and 3 poles on this side. So 180 plus 180 plus 180, it means 3 times 180. So it means that this point, this line will be on the root locus because the angle criteria satisfy that it should be the odd multiple of 180 degree. So if you take the sum of all of these angle s plus 2, s plus 2, s plus 1, similarly s, so it turns out to be 3 times 180, that is 540 I guess, and this means that this is the odd multiple of 180, and therefore the negative real axis between -2, you can see that this is at -2 up to infinity. This point will be on there up to -infinity. This point will be a part of the root locus. So we have derived this equation and we have done this up to this part. Now let's continue our discussion. The third step in basically the construction of root locus is to determine the asymptotes of the root locus, that is the root loci when the s is far away from origin. So we have to find out the asymptotes. Now what is asymptote? So asymptote is basically a straight line approximation of a curve. So if you see that this is your actual curve that is shown to you in this line, and asymptotic approximation will be approximately equal to this straight line. So this is your asymptotic approximation of this curve. So to find the asymptotes of this line, because you know that roots are basically moving on the axis, so it doesn't mean that it will only move on the real axis. It is also possible that root might be travel like in this form. So to find out these forms, you have to consider a straight line first. Then this is known as asymptotes. So you have two things. The first one is the magnitude and the second one is the angle. So the first one is the centroid of the asymptotes, that at which point the origin is lied, which point will be there for the asymptotes to take off, and what will be the angle at which it will take off. So there are two things. One is centroid of asymptote and second one is angle of asymptote. To find the angle of asymptotes, there is a formula, and this formula is again the same formula, that is sum of the angles divided by n minus m, and n is basically your number of poles and this m is your number of zeros. So if you have any number of poles in zero, you just subtract it and divide it by the actual angle, you will get this number of angle of asymptote, that how much angle the poles are leaving. And for let's do a quick example. So for a transfer function, you can see that this k divided by s plus 1 into plus s plus 2 approaches when s is, approaches to this thing when s becomes much larger. So if s is too much high, so this one basically you can ignore of both of these, and it becomes one quantity. And one quantity means 3 times this q, or this you can call it as this quantity becomes equal, and you can take a complete square at this side, and you know that this and s is very large, so the angle condition for this should be equal to 3 times of angle s plus 1 should be equal to plus minus 180 degree. This is the same formula of the angle that we used previously. So it should be the odd multiple of 180 degree, and if you divide 3 by 0, you will get 4 asymptotes. You can see that plus minus 60 degree, plus minus 180, plus minus 300, and plus minus 420, depending upon the value of k. So you are basically putting 4 value of k as 4. You can since the angle repeats itself is varied, and the distinct angle for the asymptote are determined as 60, minus 60, and 180. So the asymptotes will be 60 and minus 60 and 180 degree plus 180. So you will have only 3 angles, because after that the roots will repeat itself. So there will be repetition of the same angle, so the angles will not be distinct. So that now we have to move forward, and we have to determine the asymptotes on the root locus. The second thing was the point at which the root locus will start, or you can say the root locus will generate, or you can call it the centroid of asymptotes. The formula for that is basically sigma is equal to summation of poles minus summation of zeros and divided by the number of poles minus number of zeros. So summation of all poles minus summation of all zeros divided by its frequencies will be giving you the centroid of asymptote. So, and this point will be on the real axis. Make sure that this point is not on the real imaginary axis. This is on the real axis. So for this kind of equation, you can see that let's find out the first find out the angle condition, and the angle basically turns out to be, you can see that the angle was this was the asymptote's angle. And now let's find out the centroid of this root locus. So this is equal to, you can see that this was the number of poles, summation of poles minus summation of zeros. So summation of poles were this 0, minus 1, minus 2 and minus summation of zeros. So there are no zeros, so minus 0, and divided by there were 3 poles and there were no zeros, so 3 minus 0. So minus 3 divided by plus 3 gives us minus 1. So you can see that the poles are basically originating at minus 1. So it will be leaving you can see that the poles will be leaving at this side at the angle of minus, you can see that 60, then minus 60, and the last one will be 180. You can see that this. So this will be the centroid. This will be your angles of asymptotes, and this is the centroid of asymptotes. You can see that the centroid of asymptotes is denoted by alpha and sigma, and the value is basically -1. And there were three angles: 60, minus 60, and 180. So it doesn't mean that at 180 degree the poles will be shifting over here, because this will be not the part. You know that already, that we have also discussed that you have to make sure that the angle criteria is satisfied. So at this point, this was in spite of the fall of this and the root locus, it will not be a part of a root locus. Roots will not be coming over here, because this part does not satisfy the angle criteria. So the roots will be moving along this path, from this path towards this path. Now let's talk about another quantity that is known as the breakaway or the break-in point. So if the roots are coming from higher regions, let's say from any other point, so we want to see that okay, these roots are going in this direction. Now we want to see where it will land, where it will come back on this real axis, or if it will come or not, if it is going in this direction, or if it is going in this direction, or it is going coming downward. We want to see its direction, that at which point this root will fall in on the real axis. So that is basically a break-in point, or if here it is going out, so this will be known as breakaway point. So we have to make sure that this formula is basically satisfied. The breakaway or break-in points can be determined from the roots, and you have to take the derivative of the gain with respect to s and equate it to equal to 0. So it should be noted that all of the solutions of derivative of k with respect to s is basically 0 correspond to the actual breakout points. If a point at which this derivative of k with respect to s is not is 0, so this point is on the root locus, and it is actual breakaway and or break-in point. So let's do a quick example, and by which you can understand at what I am talking about. So you know already the characteristic equation is equal to 1 plus g of s and h of s. And let's say, for example, this is a unity feedback system, and this h of s is 1. So g of s will be turned out k divided by s into s plus 2. And if you shift, you have to equate it equal to 0, and you have to shift this 1 on this side, so it will become -1. Now you have to take the derivative, you have to move this whole stuff at this point. After that, you will have to take the derivative. You can see that now you got this equation, k is equal to this minus sign multiplied by this whole thing. So if you take the derivative now, so it will be something like this. Derivative of k with respect to s is will be equal to the negative of the derivative into this term. So if you apply the product rule of multiplication over here, you will get something like this. And now you apply, so you will get such equation. You are now getting this equation. Now you have to equate it 0, and you have to find the points of s. So if you solve this equation to find the value of s, you will get two values of s, because you know that this is a second order degree, and it means that there will be two roots for this equation. So there are two roots. So the first one is minus 0.4, and the second one is minus 1.5. So it means that what does this points give the information about? So since the breakaway points needs to be on the root locus between 0 and -1, so you know that by the first two conditions, you know that the point needs to be on the root locus from 0 to -1, and it will not be there from -1 to -2. So automatically you can judge that by using the first 2 points, that between these 2 points, this point will not be on the root locus, and this point will be on the root locus. So this will be your breakaway point. So the breakaway point will be at s is equal to minus 0.422, and this corresponds to the actual breakaway point. And this point will not be on the root locus, hence this point is not the actual breakaway or break-in point. So this point will be the breakout point, and this was your asymptote. So this was your asymptote, and this is your actual breakaway point. Now the next step is to determine the points where the root locus crosses the imaginary axis. We want to see that at which point of this imaginary axis, the root locus, this line will cut this imaginary axis. At which point? So to find that point, you have to follow this equation, but before that you have to basically apply some tools of substitution. So let's consider this S is equal to J omega, and this J is the imaginary equation, the term and imaginary part, and we have to equate both of the real parts and imaginary part to 0, and then solve for W and K to find different points of the imaginary axis. So we have to put S in and this J omega instead of S, and now we have to put this J omega instead of this S, and now we have to solve this to find different values of omega for different values of K. So for K is equal to 6, you can see that you have to equate both of these equal to 0. So if you equate this term equal to 0, you will get this equation, this K omega divided by minus 3 omega square is equal to 0, and if you compare this with 0, you will get this. From this you are getting the value of this omega, and that turns out to be plus minus under root 2. So this omega will be plus minus under root 2. So if you put this omega plus minus under root 2 equal to this equation, in this equation you will get the value of K as 6. But if you put this omega as 0, so you will get the value 0. If you put this 0 on this equation, from this equation you are getting actually two values of this, three values of omega. So two values are this plus minus under root 2, and one value is this 0. So there are three roots of this equation. Two are these, and one is this. So by putting the value, you will get the value of this K. The first K is at 6 and the second K is 0. So it means that at K is equal to 6, this will cut this part, and if you increase the K, it will further increase and take the roots on the right half plane. Similarly, it is the same scenario over here, because this will be symmetric. This will fall under the category of symmetrical modulation or models. You can see that. Now this is the graphical representation taken out from MATLAB. So you can see that this at point minus 2, this is the same example. This point at minus 2, it will follow this path, and there will be no root locus at this point, and between this point minus 1 and 0 there will be a root locus. So let's do a quick example to find the breakaway and break-in points of this equation. So the characteristic equation is given to us, that is KGS of H of S, and this is the equation. So let's find out the solution for that. The first thing is that you have to equate it equal to minus 1, because you know that 1 plus, you know the drill, 1 plus G of S of HF is equal to 0, G at H of S is equal to 0. So if you take this minus 1 on this side, you will get something like this. So you have to equate it minus 1, and after that you have to find the value of K. So the first thing is done. Now you have to take the derivative, as you all know the drill. So you have to take the derivative with respect to this S, and you have to equate it 0. Now you have to find the value of S. So if you solve this giant equation, you will get this value, and you know that this is a second order equation, so there will be two possible values for this S. So the first value is minus 1.5 and the second value is 3.82. So you have to solve this to find the which points are basically satisfying the angle criteria. So if you draw this diagram, you can see that there are now several these poles and zeros as well. These are the poles and these are the zeros. So you have to make sure that all of these is turns out your this thing into odd number of 180, odd multiple of 180 degree. So if s is equal to minus 3, so the angle of s minus 3 plus the angle of s minus 5 plus the angle of s plus 1 plus the angle of you are now sitting at 1.5. You are sitting at now 1.5, 1.45, and this will be by your this side at 180. So this will be at 180, this will be at 180, this will be at 180. And so let's draw the poles and zeros. So the first pole will be at, you can see that this will be at minus 3. It means that it is on this point. This will be a 0. So another 0 will be on 5 somewhere here forward. Let's say here is 5, and there are two poles. One is at minus 1 and another is at minus 2, and the breakaway point you got was minus 1.45. So it was something like something here. This point is at 1.45. So you can see that there are three things at this point at 180. Three things at 180. Three basically poles at this roots at 180 degree and one root at 0 degree. So there are three roots at 180 degree and one root at 0. So you will get the actual value of 540. Similarly, if you put the value of s when s is equal to 3.82, it means this 3.82 indicates that this point will be somewhere. If you take this line further forward, I will just highlight it for you. If you take this point much further, it will get here you will get 3.82, and if you find that, you will also get this thing because one of the 0 is on the that side as well. 0 will be ahead of that, so here it will be 3.82. So there will also be 180 degrees, so you will also get the odd multiple over here as well, at both of the points. So now this is the perfect example. So the first root was at minus 1, the second root was as minus 2, the first 0 was at plus 3, and the second 0 was at plus 5. One point of this breakaway is one minus 1.45, and the second point is at 3.82 between these 2 points. So it means that if you draw this on the MATLAB, you will also get this kind of curve. So this is the pole zero map according to the MATLAB, and the example is on the book on the page number 293. So you can also do that. You can also solve this equation by using the help of MATLAB, and if you want the solution, I can also provide you the solution as well. So that's all for today. I hope that you have learned quite a lot about the root locus. If you have any further questions, you can ask me in the class, or if you are not able to attend the class because of any reason, so you are welcome to ask me that questions on the email or on the portal as well. Thank you very much. I'll see you in the class. Allah Hafiz.